afternoon, everybody. Tonight's speaker is Dr. James Brucey, the Professor of Computer Science and Lead for AI for Cyber Physical Systems with the Centre for Data Science at Coventry University. He's going to kindly talk to us about reinforcement learning for optimising electric vehicle climate control systems. So, James, thank you very much for talking to us. I'll pass over to you.
Hi. Okay, so just give me a second to get my screen shared.
Oh, I forgot to ask, how would you like questions at the end or mid-flow? Or
so if you're desperate to ask a question, please go ahead.
Okay, thanks.
Okay, so just check to see that you can see my screen okay.
Yes, I can see it. Hopefully everybody else can.
Okay, great. Okay, let's get started. So I just want to talk to you about why reinforcement learning is exciting. I think that it probably was exciting to me 20 years ago and only just now becoming exciting to other people. So let me just tell you a little bit about reinforcement learning and try and explain how it could apply to, say, vehicle comfort control, but probably could be applied to a lot of other problems as well. So I'm just going to give you an example of actually the type of problem that you might think of for a control system, maybe an autonomous control system even. Think of the helicopter, right? So an ordinary helicopter will have this setup. You have the blade rotating a particular way. This produces a torque force on the whole aircraft in the other direction. And then you have a tail rotor to compensate. So when you talk to helicopter pilots, they'll tell you that it's a skilled operation to actually correctly control a helicopter because you have to both compensate for the twisting motion that's caused by the blade. Now, not all helicopters are like this, but that's probably another story. So that makes this particular video quite remarkable. So what's happening here is this is actually an autonomously controlled helicopter, and it's doing a series of stunts. I'm just going to show you one here. That was referred to as chaos. And basically, it's a whole set of twists and turns. And that's all been done in about 2006 with reinforcement learning. Okay, so let's try and understand what reinforcement learning is about. It's a separate discipline from supervised machine learning, if you've heard of that, and also from unsupervised machine learning, which usually people only think of supervised and unsupervised, but reinforcement learning is actually quite different. And you can think of them as, so, supervised is making a prediction or classifying an image as a cat or a dog. Unsupervised learning is maybe finding clusters, and reinforcement learning is trying to take action in the world. So very much in the line of control systems. Okay, so let's go through some simple definitions. Hopefully this will make the corresponding discussion a little bit easier to understand. So policy is a term used to talk about how the agent behaves, the mapping essentially from each possible situation to an action. And it's a complete set, generally speaking. So you have a complete mapping from all possible situations in some way to the actions that would be taken in that situation. So the second point is reward function. So this defines the goal of your problem. So whatever you're trying to optimize or get right. And it could be an immediate reward that is just saying, well, it's defined in terms of the immediate reward, I should say. And it's specific to that particular situation. So you could think of it like, in some cases, you would define a game as being successful when you've actually won the game. Taking a piece in chess does not necessarily win you the game, but finishing the game, putting the opponent in checkmate does. And so generally speaking, you you would tend to define the reward very sparsely as, well, you've won the game, rather than say, oh, well, you managed to obtain a piece. If you do it the latter way, then you won't necessarily get something that's optimal and might not actually win games. Okay, and then the next thing that you need to know about is a value function. So value function is basically saying, what's the long run desirability of a particular situation or state? So you might be in a particular situation. So for example, a position on a chessboard. And the question is, how good is that position from your point of view? And that may be an estimate of how likely you are to win, for example. In terms of reinforcement learning, because it has a theoretical basis, there's a very specific way to define it, and it's essentially the expected long-term discounted reward. And I'll talk about that more later. Okay, so the next point is a model, right? How the environment responds to the agent's actions. So for a chessboard, that's how the pieces move. And depending on which area of reinforcement learning you're talking about, the model may be strictly defined, or it may be learnt from something else like the real world or a simulator, or it may be even learnt internally. You may learn an internal model, and that's sort of a more advanced approach. Okay, so the model, what it does is essentially maps the current state and an action to the next state. And you typically need to define, in terms of these definitions, you need to define what are your set of states for the particular problem. That's all the possible positions of the chessboard, for example. And what actions, so moving a piece, for example. Okay, so I'm going to sort of skip over this a little bit, but it's sort of like a little bit of a flashy explanation of a particular problem that's looking at a grid world and saying, okay, well, what happens in each case? We've got some particular position, and then we get a policy, which may be sort of a default policy. And then gradually what we're doing is going through a process of estimating the value of that policy with respect to our environment. And let me just stop this for a second. And then improving the policy as we go along. So this final little bit, we've just done an additional thing, which is to change something about the reward function, basically give you a -10, essentially falling off the cliff here, as it were, falling into this hole is extra bad. And this causes the policy to change eventually until it actually tries to steer completely and utterly away from that point. Now, I did go over that a little fast, but I think the main point is I'm trying to just give you an idea of something here. Okay, so here's an example problem that can be dealt with reinforcement learning, and this is called an inverted pendulum or cart pole problem. And let's just define some things that are going on here. Essentially, the idea is you've got a pole that sits on a little cart, and there's no way to sort of control whether or not it stays vertical other than just moving the cart forward and backward, and you're trying to keep it balanced. And so we need to work out, well, how do we define the state, for example? Well, the state can be defined in terms of the angle of the pole, the momentum, the angular momentum of the pole, the cart position, and its velocity. So that's enough to define state. Basically, one of the characteristics that we're looking for in the state is that it's enough information to work out what's going to happen next if we know what action is performed. And the actions here are force, the amount of force that we're applying to go left or right. So we're trying to accelerate the cart left or right, for example. Now that won't cause an instantaneous change to the velocity, but the point is that we'll be able to gradually change the velocity, and then hopefully we can get to a stage where we've got here, which is that it's able to keep the pole balanced indefinitely. And finally, the reward function is just simply a +1 for every time step that the poll is kept upright. And that's enough information. So if you drop the poll and you lose, and your total discount reward will be based on it's seemingly infinite, but the discount means that it's not infinite. Okay, so if we were trying to play football with robots, then the question would be, where are we on the pitch? Where are the other players? Where's the ball? And what actions can we take? So, for example, there's movement actions. There's grabbing hold of the ball. You see, it's actually got like almost a sucker mechanism that grabs hold of the ball with it. And then, of course, kicking. You can kick the ball. Then there's a big question about how do you phrase rewards. So from a sparse reward point of view, you'd have 1 for a win, 0 for a draw, and -1 for loss. And there's a lot of theory about how to improve learning to make it so that it's able to learn a good strategy when you've got such sparse rewards and such long times between actually gaining rewards, which I won't go into here, but just to let you know that that exists. So where does reinforcement come from? Well, very much from psychology, the idea that we can have in our brains that we get some reward for doing something that gives us food. And that's built in partly because it enables us to keep feeding ourselves. We wouldn't have evolved this far. We wouldn't have survived as humans if we didn't have that built-in reward mechanism. Okay, so quite a long time ago, the theorist W. Gray Walter, came up with this idea that maybe you could actually build very simple robots that had the same sort of mechanisms. And this is a sort of quite surprising video to manage to find this on YouTube. But I won't go into that in too much depth, just to say that simple mechanisms are able to do quite intelligent things. And then add to that, from the theoretical side, Richard Bellman came up with the idea of dynamic programming and essentially formalized it in this set of equations, which are essentially saying that we can consider the problem recursively. So we don't have to worry about the whole possible path of next steps, but actually we can summarize it in terms of, well, we need to do as best as we can in the immediate terms of the immediate reward that we get right now, plus maximize our long-term discounted expected reward based on where we get to in the next state. Okay, so the first work to suggest actually this idea might be, well, not that you could have sort of robotic systems that could actually learn something, was from Barton and Sutton, Sutton and Barton, I have to say that wrong, and also Anderson. I think Anderson was the PhD student here. And they came up with this idea of an active critic, which, again, I won't describe in too much detail. I'll just give you an overview. The idea is that you've got this idea of some sort of value, the long-term value of where you are, but also you have a policy where what action you're going to take in a particular state. And when you find this, what's called a temporal difference error, basically the difference between what you got and what you thought you were going to get, then you use that as a mechanism, a feedback mechanism, to update both your value function and your policy. And although this was quite simple, what they were showing was that it could learn how to act, and that is the sort of key idea. So the tying back to the theoretical world of Richard Bellman and the Bellman equation was done by Watkins in his PhD thesis from 1989. And he essentially developed a technique called Q-learning. And the main innovation here is, rather than think just in terms of the value of an individual state, think in terms of the value of a combination of being in a particular state and taking an action. And that changes the problem into something that can actually be learned without necessarily having to know how the model, how the universe reacts to an action. You don't have to look at the value of all possible states that you could have got to from a particular action. You can just look at this one state action value. So really, the next major innovation that occurred was by Tesaro with using the problem of backgammon. And I suppose what's sort of surprising here is that this was the first approach to try using neural networks. And previously, people have been unsuccessful using neural networks in this, alongside reinforcement learning. There's some technical reasons why, but it meant that the more recent inventions have been quite dramatic and have helped a lot to generalize the approach. But the summary would be that backgammon is simple enough, it has such characteristics that it actually worked really well for neural networks. And essentially, one of the nice things about this particular game and their solution, Tesaro's solution, was that it suggested different ways of playing the game that were not thought of by expert players. And more recently, there's been ties to the parallels to dopamine. So there's some essentially work saying that the mechanisms in terms of equations that are going on in dopamine are actually incredibly similar to the mechanisms that are going on in temporal difference learning. Okay, so I personally had some involvement in doing work for RoboCup. You can see a very old robot now, but was handcrafted by our university at the time. And we were initially doing code by hand. So you basically say, how do we get this robot to move to a particular location? So the location, the target location here is marked as a green circle. I don't know if you can see that, it might not come out very well. And the initial location is the red sort of box, basically saying where the robot is. And also it had some initial velocities, so it's indicated by the red arrows as well. And what you tend to get is this sort of behavior, that when it tries to get to a target point, that it tends to have to stop, swing around, maybe overshoot in terms of swinging around, readjust, and then come back eventually to the target point. And that's really because when you have existing momentum, it really changes how you should behave. But of course, that's very hard to take into account when you are programming this by hand. So that was why it was a nice surprise to find how well reinforcement learning can do the task. And actually, it was very close. Well, I also managed to, for a simple problem, show that it was close to the optimal solution. Okay, so I also did some work on other behaviors that the robot had to do, which is in terms of dribbling the ball, and you can see sort of how well it did by hand, which is not very well. It was very, as you might call it, robotic and unresponsive to the change in the ball position. And then you see this much more dynamic and reactive approach from reinforcement learning. Still not perfect, and probably could have, you know, if we were going back and doing it now with faster computers, it would probably be much more successful. Okay, still around this time, this was when Andrew Ng and Pieter Abiel produced their wonderful helicopter that's probably one of the first demonstrations of using reinforcement learning for real robotics. And I think what this is demonstrating here is just the range of things that the reinforcement learning system could do. They were saying, okay, well, let's get it to learn how to do each of these individual behaviors, stationary rolls, tick-tocks, etc. And then they would string them together. So it'd say, okay, now do a stationary roll, now do a steady flight. And I suppose the point about this is that to get this to work, they had to do a really clever trick, which is to do with understanding the physics of the helicopter. And I'll talk a little bit more about that later on. Okay, so, or if I don't, please remind me. Now, you may have heard of this one as well. So this is a bit more recent, 2016, or maybe even a bit earlier than that, actually. The Google DeepMind published a wonderful paper in Nature that essentially showed that they could solve a huge number of the Atari 2600 programming games by just looking at pixels. So ordinarily in the past, this would have been done by having the computer look at the data in the back end and be able to work out the best policy. But this is actually just looking at the pixels. And I think even to the point where to work out what reward it's getting, it's actually interpreting the pixels at the top of the screen. So that's a really nice demo, and probably the biggest success in terms of games has been solving Go. I remember going to a conference some time ago where people were saying that Go will never be solved because the branching factor is way too high. And what this showed was actually it's completely possible, and that we just need to be thinking about the problem in a different way. And I think that's one of the nice things, that we do really need to start thinking about problems that we have in our world a different way. And one of the options to look at them differently is reinforcement learning. So here again, another example of applying this to quadruped robots. I haven't updated these slides recently, because otherwise I would have included some wonderful work by I'm not too sure the name of the chap, but he's doing a mechanism called Dreamer. But what you can see here is that when you ordinarily translate from simulation to real world, it doesn't work. And what they needed to do was to go back to the simulation, fix the simulation, and then they found that actually it was really successful and did something that possibly they hadn't even expected. Now, OpenAI managed to get a robot hand to solve a Rubik's Cube. And in a way, this is extremely impressive. It's impressive for a number of different points of view. They need to develop new techniques for what's referred to as domain randomization to deal with the fact that the real world is always slightly different from the simulated world. This is a sort of great demonstration of the power of this approach. The problem is that this was really costing them a lot of money, and it wasn't likely to produce any interesting results anytime soon. You know, there's no real payoff to getting a Rubik robot to solve the Rubik's Cube. So when we come to applying reinforcement learning to real-world problems, I think what we need to try and do is to do these sort of 4 things. And let me just talk about them each in detail. The first one is that it's really helpful if we have a common framework. And if you're going to start working in reinforcement learning, there are actually a number of frameworks going. More recently, I would recommend what OpenAI Gym evolved into, which was Gymnasium, and that's supported by Farama. You need to be clear about the problem definition, of course, as well. And that means that everyone's trying to solve the same problem rather than saying, okay, well, I changed the problem slightly and all of a sudden I get a huge amount of success. That obviously doesn't work. And you need to be able to resolve the problem of the environment. How do you simulate the environment? So we're seeing that issues with the differences between the simulator and the real world can actually be quite challenging. With the helicopter, for example, they were facing the problem that you have fairly complex complex differential equations that need to be solved to just forward the time step by 1 millisecond. And naturally, that would lead to an extremely slow process. So inevitably, even if you do the best equations, the results don't fully match the real world. Why? Because there's friction that you didn't know about. There are other little effects in the real world that are happening that are not necessarily catered for within those equations. We also need to be collecting data, and that means that we need to have hopefully open data sets. Unfortunately, lots of data collection occurs privately, so I think, you know, if we press for anything, we should press for making sure that all scientists are aware of the importance of open data. And I think also we need to consider human elements. So one of the things that control theorists don't tend to worry about is the human in the loop. And the main reason that they don't worry about them is because they can't solve their equations if they do. And so what do you do? Do you just ignore the human element, or do you have to incorporate it in some way? And I think reinforcement learning offers a real opportunity to actually consider the human element in processes. Right, so now I'm just going to talk about some stuff to do with my own work, which is to look at whether or not this approach could be applied to extending the range of electric vehicles. So the issue here is that, you know, in a reference test, for example, with no air conditioning, you have quite a long range for your electric vehicle. If the sun is shining and you need to run the air conditioning, you might have a certain percentage drop in your range. And then it's even worse in cold weather. So what do you do? So obviously, one of the things that you want to do is to try and avoid unnecessary energy use. But how exactly? And my answer is by doing better control and by controlling the right thing. I think this is two elements that we need to take forward. So when we say controlling the right thing, well, think of seat heating, for example. At the moment, the seat heater that you probably got in your car doesn't actually integrate with the rest of the climate control system. So your climate control might be set to 22 degrees, but it doesn't vary just because you've got your seat heating on. So it doesn't allow for the fact that you probably don't need it quite so warm when you've got seat heating. And also there's an opportunity from the point of view of natural ventilation. Very common to have situations where you get into a hot car on a hot day, but actually maybe the air temperature outside is quite cool. And I'm giving an example here from of a building in Coventry University, which was quite innovative for its time. It's a very nice building. But also the idea is coming from Australia, I think, where they tend to have, they tend to make use of natural ventilation to use external air to cool the building down up to a certain temperature, and then they close windows and start running the air conditioning system only when it's very hot. And it's obviously an opportunity for saving energy. So I've been working on this system for a while, and that has sort of led to an Horizon 2020 EU project, which was done with these collaborators. And essentially what we were trying to do was to look at the climate control as a reinforcement learning problem. And there's many aspects to this. I won't go into a lot of detail here, but just sort of relatively quick overview of the idea. So the main problem that we had when we started was this issue of those differential equations that you've got for defining what goes on in your environment. We would really want to be able to have that solved much faster. So what methods could you use? So one possible method is suggested in the next slide. So, but I'll just mention the problem that we have here. Maybe we need about 8 years of simulated experience. That doesn't mean we're simulating for 8 years. That means that we need something that extremely fast simulator that can simulate hundreds of runs simultaneously and be doing them in microseconds, not seconds of time. And the problem is that it takes a three-dimensional computational fluid dynamics model about 10 minutes. So that's a quick, I think, guesstimate to simulate a single second of simulation. Ordinarily, that's not what people use in the car industry. They're using what are referred to as lumped thermal models. They're still quite slow, though. They need to simulate quite a lot of the aspects of the car cabin. So, for example, the amount of thermal insulation you have in the doors or in the roof, the different characteristics of the glass. And so they still end up with quite slow simulators. So what we did was we gathered data, and we had sensors in the seat. The sensors you can see are a combination of thermocouples and black bulb sensors. We also had air velocity sensors. And then we found a nice way to accelerate, essentially by learn the cabin model from data. And again, I'm just going to gloss over the detail here, but I think it's a nice idea. And actually, the more I look at it, the more I find that actually it's a lot of people are converging on this approach. The nice part about this particular problem is that it's linear in terms of its differential equation, if you can ignore radiant heat. And so therefore, that means that you can model the differential equation with a linear model. So what do you end up with? So this is an example of sort of simulation estimates. What's happening here is that we've given the simulator the initial state of the car and also all the actions that we took throughout, what temperature sensors were reading on, say, the outside of the car, the things that the simulator would actually know, and then we're able to simulate how the temperature changed over time. So, and you'll see that these curves match up pretty well. I mean, with a few small exceptions, they're doing pretty well. And in particular, the yellow and blue line, I think, are for the footwell, and you'll notice that's hotter when the car's being air conditioned. That was a little bit high, probably because the air wasn't being directed in the first bit, and then when the temperature, when the car is left to its own devices, then it gradually heats up under the solar load that it was under. And of course, the head temperatures, which are the upper part, they get quite hot. You can see that it's getting almost to 70 degrees temperature. Okay, so how does this simulator go? Well, it's pretty good. It basically gives a normalized RMSE of about 1.8% overall, about 0.4 of a Kelvin for across the front bench temperatures. In comparison, it also takes about 5 microseconds to compute each second. So we can simulate a year in a few minutes. So from using RL in the past, we've got sort of these preliminary results, and I think I actually got more up-to-date results in terms of these approaches. So this is just to give you an idea about the domain, and I'm hoping you're going to ask questions, things that I've glossed over that you're interested in. What I probably want to sort of settle on is essentially the idea that this is one of those areas where everyone will tell you this can't work, and they'll tell you why it can't work in a lot of detail. But I think what we're going to find is that whether or not it's me making it work or somebody else, that this pretty soon will be the de facto way people are having their control systems built for things like climate control and many other things. So thanks very much for your time, and I'll open for questions. I'll leave the slides just up just in case you want to refer to them.
So has anybody got any questions? Meant silence. I was involved in a discussion with some friends about electric vehicles, the motors, they seem to think that there was a necessity to cool the motors to stop them overheating, and that some of that heat could then be used to heat the cabin. Is that something that you're aware of?
So you're talking about using the waste heat from the motors.
Yeah.
And that's actually the predominant method for heating in ICE vehicles. So that tends to be what people did. The negative part of that is that you may not have waste heat available. So you generally have to supplement that with some other mechanism.
Is there no waste heat in electric vehicles?
There's a whole lot less waste heat.
Presumably because electric motors are more efficient than ICE engines. Yeah.
I'm afraid I'm not an expert in the heat profiles of electric engines.
Yeah. Anybody else?
May I ask you one question?
Yes, Yuri.
Thank you. You mentioned on one of last slides fuzzy logic systems, which is used for temperature control. Yes, thank you. My question is, I'm not specialist in this reinforcement learning, but I know what is it fuzzy logic. My question is, what is your opinion? Maybe your results in reinforcement learning can be added to fuzzy logic control in order to adjust coefficients of fuzzy logic algorithms in order to make maybe more smoother response. Because fuzzy logic basically works on off, really quite rough. But maybe reinforcement learning can make a better response.
It sounds like you've got a possible research project that you want to investigate, and I wish you the very best of luck with it.
Oh, thank you. No, just another question. In the beginning, you mentioned about the Bellman's dynamic programming. Some time ago, I derived equations, really extremely time-consuming process. It took me around 7 pages to write these equations. Basically, how it works, you must know the exact path from A to B, and you derive in opposite direction from B to A in order to give the optimal path. After that, your vehicle, autonomous vehicle, will move on this exact path which you calculated. But in real life...
Sorry, I just interrupt you for a second. I'm having a little bit of trouble hearing you. I don't know.
Oh.
I'm going to just try and change my sound setup so that I can try and hear you better. I do apologize. Just I might need to get you to repeat the question. Could you try now?
Right. You mentioned Bellman dynamic programming in the beginning. Some time ago, I derived equations for dynamic programming using this Bellman theory. How it works, you need to know exact path from A to B, for example, on the road for autonomous vehicle, for example, to deliver milk to house. And right, so basically, you need to calculate in opposite way from point B back to point A. After that, you put this calculated path in memory of computer, on board computer, ECU, for example, and autonomous vehicle will follow for this calculated path from A to B, because you already pre-calculated everything back from B to A. But in real life, everything can happen. Some obstacles can change this pre-calculated path. Again, maybe reinforcement learning can just solve these uncertainties.
Yeah, so I guess this is very much dependent on how you formulate the problem. So if I can try and state the issue back to you, and maybe just let's get this.
James, we've lost your sound.
Can you hear me now? You can't.
Yeah.
Oh, okay. Yeah, no, I think I was just thinking about how to express it.
Sorry. Well, there was a funny noise and then you went quiet.
Oh, right. Yeah, okay. Let me just.
Someone pulled the plug out.
Yep. Somebody pulled the plug out. Probably what happened.
Yeah.
So, I mean, this is sort of a characteristic of the sort of problem that you're referring to, which is that traditionally, from if you're defining a dynamic program type problem, that you would have an exactly known environment with specific states, and you would know everything about that world.
Yes,
right?
yes,
So
correct. Yes,
called fully observable. And I mean, this has often been seen as a big deal that maybe we can't apply reinforcement learning because we require fully observable environments. And I think that while that's somewhat the case, I think it's actually I think probably this would be if I was supervising a PhD student, then I would go into depth about this aspect. But I think from the point of view of this talk, I probably shouldn't. But just sort of to give you the rough idea, part of the issue is to do with how you formulate the problem. So whether or not you're actually dealing with a fixed world, because you could be reacting to give you an example, when you have a robot that's seeing an area and it says, okay, well, I can move forward because I've got space in front of me, and I can move to the side, and maybe it's actually got a target location that knows is off to the northwest, and maybe it has some other information about obstacles, right? That's different from this formulation here, which says basically these are exactly the states that you can go through, and we have exactly the probabilities that will occur from each transition, right? So definitely, if you're talking about dynamic programming, traditional dynamic programming that was developed by Bellman, then yes, you have to know the whole thing exactly before you do any calculation.
Yes.
That is not the case with reinforcement learning. And again, I think probably would require more time than I can give right now to give you a proper explanation. But roughly speaking, there are a number of things that are there. And one of them is to do with the way you define the problem. The second thing is to do with the use of function approximation.
Okay, thank you.
Do you have any other questions?
Everybody else is too shy, obviously.
Maybe if there's any.
So what you're saying is all this is happening in real time, is it? Or is just doing all these sums to work out and how to.
I like the way you say computers is doing sums. Of course, they're doing multiplications as well. But you remind me of my sister.
Yeah, fast Fourier transforms and all that happening in real time, is it?
No, there's no fast Fourier transform involved. I can tell you that. Depending on how you want to develop the approach. So to give you an example, the helicopter example that we saw before, the reason why that can work is precisely because reinforcement learning allows you to distill a mapping from situation to action. And
Right.
there are various ways of actually doing that mapping, but generally speaking, they're quite fast. So we're talking about a few layers of multi-layer perceptron, and that's it, and one run through. So from point of view of operations, we're talking maybe some matrix multiplications, maybe even as small as 5 or 6 matrix multiplications to do per cycle. So it's exceedingly fast. And probably the key competitor to it in current approaches is model predictive control. And the difficulty model predictive control has is that it needs to have the simulation environment entirely known. The simulation environment is fixed, so it cannot learn new things from being used in the real world. And furthermore, it needs to simulate out a large number of possible trajectories through that environment, through that space of possible worlds, to be able to optimize. Having said that, there are definitely some advantages to model predictive control, and I wouldn't necessarily say that there's a clear winner on reinforcement learning side, but there's definitely cases where reinforcement learning has very clearly outperformed model predictive control. And probably the most recent and striking case is, and you can look this up on YouTube, if you go and look for UZH, and I think they call it Reaching the Limit is the title of their YouTube video. So if you search for UZH Reaching the Limit, you should be able to find their work, which is essentially using reinforcement learning, and particularly they show why other approaches such as model predictive control don't work as well.
Thanks. So basically what you're doing is you're giving your machine experience. That in a nutshell. So like a child learns.
That's certainly a lay
catch a ball. It doesn't do all the sums. It just learns if it does that, it catches the ball. Your helicopter learns if it does a certain set of actions. It stays in the sky rather than falling out of the sky.
Right.
Is that a reasonable summary?
Sorry, what your summary?
Yeah, is that a reasonable summary? We're giving machines experience like we do with small children.
I think there's going to be some parallels between teaching children and teaching robots. Yes, but I think there's definitely not the it's not the standard approach now for training robots, and there are a lot of safety concerns associated with it. I think that those concerns are not necessarily always well founded, and I think that there's still work to be done to make sure that systems are safe.
So your robots need 3 laws, do they?
Now I think you're baiting me.
3 laws safe. Has anybody else got any questions? Come on, don't be shy.
It's not a problem if you don't. I mean, I'm easily findable on the internet. If you've got follow-up questions, you can try and email me. Although I can't guarantee that I'll be quick with response. I've got quite a lot of email traffic at the moment. But if you'll forgive me, I'm probably going to have to draw to a close there because I need to go and cook my son dinner. My wife has just gone overseas.
Oh, right. Yes, thank you.
So if that's okay, I might end there.
Brilliant. Okay, thank you very much for your time, June.